Hello, my name is Brian Mota, and today I will be going over problem number one. So problem number one is derive Bernoulli's equation starting from the rate energy balance equation. Assume the system is a control volume system and has negligible heat loss. So to start off, what is the energy balance equation? Well, the energy balancing equation that I used is the change in energy of the system equals the change of internal energy, which is delta U, plus the change in kinetic energy, plus the change of potential energy. With this, I know that in the system, everything is going to be contained. So I used the first law of thermodynamics to help me solve this problem. So first law of thermo, which means that energy can neither be created nor destroyed, and it is expressed with delta U equals Q minus W. I use this to help me solve this equation. As you can tell, you have both delta U. So the problem states there's negligible heat loss. So if there's negligible heat loss, you don't have any heat transfer. So I made this equal to 0. So now my delta U equals the negative work. So if I rewrite this, so 0 equals negative W plus a change in kinetic energy plus potential energy. I just manipulated this, added W to the other side, and I got kinetic energy plus potential energy. And here, to help explain it, we know work can't be, like actual work be done inside the flow of a pipe. What is actually done is pressure inside the pipe acts on the pipe and creates an external work. So to help explain this is we know that work equals force times distance, and then we know that force equals pressure times area, and we can plug this back in. So work equals pressure times area times distance. And if we assume that the liquid, like theoretically, like flowing through the pipe, if we assume that that liquid is incompressible, then we can state that volume equals area times distance. So we can write our work equals pressure times volume. And to help explain this, it's like, say we have a point here and point here, and liquid is flowing through it. So from this point and this point, they're gonna have different work done on it because you'll have different pressure acting at each point. So to rewrite this, or to further this equation, we're gonna put so our work, I can put here work, actually I'll put here work 1 equals our pressure 1, and our volume, and we know it's a control volume, so it's going to stay the same. So our work 2 is going to equal P2V. So if I write our work done on that system between those 2 points, I can put P1, so work 1 minus work 2 equals, I'll write this out, so 1/2 NV2 squared. minus 1/2 NV1 squared plus MGH2 minus, I'll put this in parentheses, MGH1. So I can rewrite this. So our P1V minus P2V equals all this. I'll rewrite it, 1/2 NV2 squared, 1/2 NV1 squared plus MGH2 minus MGH1. Here we can just divide our volume to both sides. And just a little side note that in case no one knows, so M over V is actually rho, which is this thing. It's like the weird looking P. I'm gonna skip a step because if we multiply or divide V to each term, we're gonna have a M over V, which turns into P, which is our density. Here these cancel out with each other, and I will rewrite this. So P1 minus P2 equals 1/2, and then that V, so there's going to be a V here, V here, V, that turns into rho. And then don't get them confused, this V, it's actually lowercase v, which is velocity, and this capital V is supposed to be volume. So just so you can't get confused. So I'll rewrite this with all the terms, V1 squared plus the PGH2 minus, sorry, let me rewrite this somewhere else. So V equals minus my GH1. So here I can add all my ones, so 1 here and then 2 here. So just combine our points together. So it's gonna look like P1, and then I'm gonna add 1/2 my rho V1 squared, and then I'm gonna add this to the other side. So 1/2, oh sorry, it's M, it's rho GH1 equals, and then I'm gonna add this side to the other side. So P2 plus my 1/2 rho V2 squared plus my rho GH2. And this is Bernoulli's equation. So that's how you derive it.